Imagine, just for a second, a state-of-the-art power plant. I mean, it is engineered to absolute perfection. It's built to withstand earthquakes, severe hardware degradation, massive natural disasters, the whole shebang. But then, despite all of that flawless physical engineering, the entire system completely fails. And why? Because of a single, deliberate cyber attack. It is a really terrifying premise, right? But honestly, it's the reality of our modern infrastructure. As robust as our traditional safety systems are, they often fall completely short when it comes to identifying and mitigating these deliberate cyber threats.
So, in today's explainer, we're diving into some fantastic research out of the Idaho National Laboratory that tackles exactly this. We're looking at how we absolutely must evolve our safety engineering for the digital age. Our goal today is to figure out how to bridge this massive gap between traditional physical safety and the very real, very present threat of cyber-induced hazards. The landscape has changed, we need to adapt, and luckily, we actually have the tools to do it.
All right, here is our roadmap for the explainer.
First, we'll establish a baseline with traditional hazards analysis. Second, we'll uncover the cyber blind spot. Third, we'll introduce the cyber-informed engineering framework. And finally, number 4, we'll look at how to upgrade our existing safety tools.
Okay, Section 1, Traditional Hazards Analysis. Let's set the baseline. Historically, hazards analysis has been the absolute gold standard in disciplines like nuclear and aerospace engineering. But to really grasp what's broken right now, we first need to quickly understand how the system was originally designed to work. The baseline rules are actually incredibly simple. Engineers look at two main things. First, severity, which is the magnitude of the harm or damage that could happen. And second, likelihood, which is the actual probability that this adverse event is going to occur. By balancing those two factors, engineers know exactly which systems need the most protection.
But here is the catch, and it's a big one. It's all about how that likelihood is calculated. Traditional models rely heavily on what we call stochastic probability. Essentially, they are calculating the random chance of independent, natural, or accidental failures. Think of things like a pipe bursting from normal wear and tear, or a valve just randomly getting stuck. It's all about natural probability. And that leads to a highly logical, standard engineering workflow. Step 1, you identify a process deviation, maybe no flow in a pipe or high pressure in a boiler. Step 2, you develop a scenario around that specific deviation. And step 3, you analyze the impact and the root cause. Ultimately, this leads to building out mitigations and safeguards. It's a great system for what it was built to do.
But that brings us to Section 2, the cyber blind spot. This is exactly where those traditional models completely fail. This is where that traditional logic literally hits a brick wall. We have to fundamentally shift our thinking from systems failing by chance to systems failing by malice. Think about it. Stochastic events are totally random. Cyber-induced events, on the other hand, those are intentional behaviors executed by malicious, smart adversaries. An intelligent attacker doesn't sit around waiting for a random 1 in a million probability of a valve failing, right? No way. They find a vulnerability and they exploit it on purpose at the exact moment it will cause maximum damage. The source material for this research puts it incredibly bluntly, and it really highlights this massive blind spot. Currently, in standard traditional models, cyber-induced or actuated events are not considered. End quote. These models assume that highly dependable, passive safeguards are somehow totally immune to interference. They are essentially pretending that digital manipulation simply doesn't exist. And let me tell you, the fallout from ignoring this reality is devastating. Look at this table. When we don't consider cyber realities, we get an incomplete identification of risks. That leaves massive blind spots. It creates hidden single points of failure, meaning interconnected systems can just collapse simultaneously. And what does that lead to? Real-world safety hazards, like catastrophic equipment failures or chemical spills, along with massive, incredibly costly operational disruptions. Which leads us to the ultimate danger of relying purely on probability. In traditional engineering, complex scenarios are very often just discarded if they have a low stochastic probability of actually happening. But an attacker, they literally do not care about your probability math. Filtering out low-likelihood events probabilistically creates a gigantic vulnerability, because an attacker is actively orchestrating a sequence of discrete events to guarantee a failure. They make it 100% certainty. So, Section 3, Cyber-Informed Engineering, or CIE. Let's talk about the solution framework. How do we actually fix this?
Well, the Department of Energy and the Idaho National Lab have put together a really brilliant solution framework known as CIE, Cyber Informed Engineering. At its core, it emphasizes using actual engineering controls to mitigate maliciously induced hazards. Now, it's really important to understand here. CIE is not a replacement for traditional analysis. Not at all. Think of it as a crucial, cost-effective upgrade. It essentially takes a cyber lens and places it right over the existing safety models that organizations are already using. The source outlines 12 core principles of CIE, and we've pulled out the absolute most critical ones for you here. Notice the heavy focus on things like engineering controls and consequence-focused design. What that means is engineers can physically design out cyber risks. Rather than just crossing our fingers and relying on the IT department to push a software patch, we can literally engineer the physical process so that even if a hacker breaches the digital network, the physical system just cannot be driven to catastrophe. It's a real game changer. Now, I want to call attention to one of the most fascinating aspects of this entire framework. That's Principle 9, Cybersecure Supply Chain Controls. Traditional hazards analysis almost entirely ignores supply chain risks. But think about it. If a vendor component or a piece of software arrives pre-compromised, you are literally installing latent hazards into your infrastructure on day one. CIE forces engineers to stop and evaluate those hidden threats before they're ever plugged in. By explicitly addressing the supply chain like this, Principle 9 closes a massive, gaping hole left open by traditional operations and maintenance methodologies. It makes sure that the very building blocks of the system, the raw materials and software you're buying, are scrutinized with a highly cyber-aware perspective. Let's move into Section 4, upgrading our safety tools and actually bridging the gap. We've talked a lot about the theory, so let's look at physical integration. If you check out the green dashed box on this diagram, it pinpoints exactly where you get the greatest potential gains for CIE augmentation. See, CIE doesn't really change that initial step of identifying a deviation. Instead, it gets injected directly into scenario development, impact analysis, and root cause analysis. This is exactly where you map out the specific malicious failure paths an adversary might take. And here is the tactical application of that integration. This is basically the golden rule of CIE augmentation. You must give no or low credit to any safeguard an attacker could potentially access through digital pathways. Think about what that means. Decades of historical reliability data mean absolutely zero if a hacker can just digitally switch off the safety valve before they cause a pressure spike. You can't trust a digital lock if the hacker has a digital key. Now, for the engineering professionals watching, the really good news here is that you do not need to throw away your existing methodologies. The research clearly shows that CIE naturally aligns with and actually enhances all the established tools you already know, like HAZOP, PRA, FMEA, and LOPA. You get to maximize your current investments while simply broadening your scope to include those cyber-induced impacts. Finally, and we really have to emphasize this, safety is never a set-it-and-forget-it checklist. Traditional hazard analysis is way too often done early in a new build and then just stuffed into a binder on a shelf. But operations and maintenance, O&M, is where your infrastructure is actually the most vulnerable. Ongoing operations have to constantly be reevaluated through this CIE lens. Why? Because adversary capabilities are evolving so much faster than our initial design assumptions ever could. So I'll leave you with this one vital question to think about. Are your traditional safety models actually protecting you? Or are they just giving you a false sense of security against a deliberate, intelligent cyber threat? It is no longer enough to just engineer for random chance. It's time to start questioning those probabilities and start physically designing out the risk.